The title of my talk is Architected Cellular Metamaterials Hold the Future of Surgical Meshes. So thanks to CAPE for generously funding the project. I'm a third year PhD candidate. I'm moving to my fourth year this October at the Department of Engineering. So let's begin. Surgical meshes are like textile clothes, which are used to support organs when they fail inside our body. Like, when you have hernia or vaginal prolapse, it requires surgical procedures and you need to place a cloth-like material to support. And it has been used for quite a long time, about 30 years. So, as you know, 30 years is a long history. So the meshes have developed over time. The present generation meshes are called third generation meshes, and they typically look like one of these. Either they're knitted or they are woven. So as I told you that they are textile-based meshes, and the mesh materials commonly used are polypropylene and polystyrene, which are biocompatible, and the major manufacturer in UK is Johnson & Johnson. So why am I doing this with architected materials? There are several drawbacks, and the drawbacks are quite serious. So from a mechanical engineering perspective, the major drawback that they have is this is the mesh that I'm holding in hand. It has different properties in different directions. That is, the properties are anisotropic. We call it anisotropic. And the problem is when you do surgical procedures, the surgeon needs to be very careful in placing the mesh, because if you place the high strength direction along a very low loading direction, then it's subjected to failure soon. So recurrences are very high. It's more than 30%. Second is these biocompatible materials like polypropylene, when you weave it like a cloth, either they can become very stiff or they can be very soft. So in soft tissues, when you place a very stiff thing, it creates a lot of discomforts. But there are complaints from patients. Third is porosity. You cannot control the porosity, the pore sizes. Once you weave it, that's it. You cannot change the porosity. And porosity is important because of infections, the bacterial growth. So these are the three major things which caught my attention, and I thought, why not try something different? The scale of the problem, yeah, it's a huge problem. NHS, if you Google it, you'll find out NHS keeps on revoking the use of surgical meshes, and then the Royal College of Surgeons comes and says, no, this is the best way that we can do. Even if there are recurrences, we have to go for surgery again. But there's a back and forth going, but the problem still exists. Now, going to the solution that I'm submitting is a cellular materials. So cellular materials are found in nature. We have been inspired by nature to look for cellular materials, and quite good examples are honeycombs and the nest of wasps. So what is cellular materials? They are open structures. You just do not create a continuous material, but instead you build like small cells. On the right over here is a good example of octet truss lattice, which is made of steel material. It's quite lightweight. You can see the relative density is quite less. There are a lot of air spaces inside. So they're quite lightweight. Second thing is the mechanical properties can be tuned. That means if you give me steel and I have a fixed strength and elastic modulus, now if I design it as different unit cells, honeycombs, hexagonal honeycombs, or maybe triangular cells, or maybe this 3D octet truss, then the unit cells will dictate the properties. So the mechanical properties can be tuned based on the unit cell. Secondly, if you change the relative density, which is nothing but you change the dimension of these cells, you can also get another advantage on the mechanical properties. And clearly visible is you can change the porosity. So these three are good markers for me to begin that, okay, why not we use cellular materials for surgical meshes? Now the methodology that I adopted is I wanted to know, when I choose a particular material, suppose I choose polypropylene, what unit cells should I decide, and what should be the particular relative densities? To know that, to come up with a very general map, a design map, I had to apply the fraction mechanics, classical fraction mechanics from continuum solids, and apply it to these architected materials. One of the interesting things that I found is these materials, as you can see, they are made up of struts, right? So when you pull those materials on this way, instead of failing or tearing, they can go into buckling, which is elastic buckling. And elastic buckling absorbs a huge amount of energy. That means if I place this mesh, which I have manufactured finally, and I place it inside the body in the lower abdomen. When you sneeze, a sudden impacts, there'll be huge load. Okay, there's a fatigue load, there's a huge impact load. Such impact loads will not cause tearing, because this lattice material can undergo local buckling in the struts, so they can absorb a huge amount of energy. That was a key finding in this study, and I did it with polymeric materials because that's what the surgeons prefer. So low density materials made from polymeric lattices, typically the yield strains are in 2%, 3% range. They will undergo buckling instead of failing. Okay? So I wanted to confirm this in experiments because this is all done in finite element calculations, and I wanted to see how accurate these are in experiments. So yeah, we have to manufacture this lattice specimens, and I cannot do a loading test in huge and strong. I had to make a small arrangement, and I wanted to see it when it happens. So it's an in situ X-ray CT arrangement that I had to build, and the loading is not just uniaxial, it has to be triaxial, because inside your body the loading is from all the directions. So triaxial loading was carried out using this setup, placed inside an X-ray CT, and this is how it looks. Can I? Okay. Can you see the video?
Yes.
Okay, so you can see this, that, oh, sorry. It's just taking a small slice from the city. The struts here have gone into buckling. So this is a sudden impact that I provide from all the three directions. And instead of failing, the struts have gone into local buckling. So all the absorbed energy are being absorbed in elastic buckling. So it delays failure, it prevents failure. This was a good point of start, you know. And then I changed the topology. I tried different topology. And one of the topologies I'm showing here is an octet truss topology. And you can see that these struts are, this unit cell is having a dimension of nearly 100 microns, and I have millions of unit cells. And finally, the product looks something like this. So this is a conventional mesh, and this is an architected because I apply an architecture in the design, and Cellular, they're open structures, and I'm designing a surgical mesh. So these are more like cushion-like materials. So what are the major advantages? Well, as I told you, the unit cell will decide the anisotropy. So I can control how much anisotropy I want based on the choice of unit cell. Second thing is stiffness and strength. Now, if I use the conventional materials, textile-based surgical meshes, then my strength and stiffness are fixed. But here, I can control it based on the relative density. So it scales with relative density. So I have better control over stiffness and strength. With the same material, changing the unit cell, changing the dimensions, I can control the stiffness. So for suppose example, I need for a very soft tissue, I can go from a hexagon, from an octet to a hexagon and make it very soft. Porosity, you can see it's very direct. You can change the porosity as much as you want. There's definitely an inverse relationship with stiffness and porosity, but that can be fine-tuned, and that's why I had to develop some design maps. So this is a fracture-based design maps. That means these contours are telling me the failure lines, okay? And I want to be in the region of elastic buckling because I want that mesh material to go into buckling whenever impact loads are applied. So suppose somebody tells me, a surgeon tells me that, you know, I want something which is not very tough, it has to be soft, and I choose a number over here, okay? Suppose 0.009 is my failure line. I will not go here, I'll go something here in this region because I know this will absorb huge amount of energy during impact loads. And then based on the porosity requirement, I can also change the relative density. And this T bar is nothing but a structural number, which I have collapsed, a non-dimensional structural number, which I have given over here. So beta is the loading biaxiality. I need to have some idea about how the biaxial loading in the intestine will be. I need to know, you know, what will be the different crack sizes inside that. And then I can decide on this parameter T bar, the normalized, and the porosity, and I can, okay, choose this or this, any point, and design the mesh and give it to the patient. So this are design maps which I've developed. And this can be generated for different topologies, for different yield strains, but they're quite generalized. I mean, you can use it. So when you give it to a manufacturer, you can give this design map, they will know the requirement, they will choose the parameters and just print it. So currently I'm writing a research article based on this because this is not part of my PhD. I mean, it's an extended work which I did. So it's taking up a little bit of time. I need to do a few more experiments and I need to fabricate a few more mesh and do experiments because they would want more experiments and submit the draft. I'm also applying for clinical approval with the Royal College of Surgeons of England with the help of NHS. And Addenbrooks have been quite helpful in this. And finally, patented the design and name it as architected cellular surgical mesh. And on the research frontier, there's something called hierarchical structures, which are becoming popular now. Now, all this was not possible in the last 2 decades because it's just recently that you can print such small features and scale up to big materials, full-scale material. So hierarchical architecture is something which is not yet possible, but theoretically we can study and see, can hierarchical structures help even more? So yeah, I mean, I'm in a stage where I've completed the project and I'm writing a research article, and let's see what happens. Thank you.